AIC might be a somewhat better criterion, but I'm not sure what if that's just the personal experience of this author, or whether there's actually some theoretical.
I guess I was just wondering, like, if you know that minimum ARC or BIC is sort of your goal, and in situations where like the computational penalty associated with looking at sort of all models within reason is not that high, why not just do that? It seems similar to some like other things that we've done here, where you look for sort of you plot all the different options.
Right. Right. Well, so yeah. So before I ask that, anybody else have any thoughts about why that might or might not be a good idea?
Sorry?
I mean,
why that might, why doing what Eric suggested is might or might not be a good idea?
I don't know.
You play devil's advocate and say that it's sort of you're being agnostic about like the structure of your data. You're just saying like you're ignoring things that you may know about your data that would affect how you would model it.
That's one piece. Another piece is that the AIC and BIC, because they're based simply on the log likelihood, they're just looking at essentially the sum squared residuals as their measure of goodness of fit. So they're not taking into account other aspects of the pattern that might be in the data or even in the residuals. But I don't know how important that actually is in practice. I mean, it may well be that the model that minimizes squared sub-squared errors actually, and is subject to the constraints for a number of parameters, actually is pretty good. And so that's kind of an empirical question. What would I say to that? So one way to approach that might be to run all the models, and instead of simply having the rule take the one with the best AIC, to take the cluster of ones that are closest to the best AIC and look at those and see if it makes sense based on these more qualitative pattern matching views of the ACF and the PACF. And also looking at the residuals from those models to see if there's pattern left over. But this is actually an important piece too about model selection. I don't know I don't know the theory behind the Bayesian information criterion, but the theory behind the UK information criterion AIC. The notion there is that there's what is there? There's truth. Okay, it's unknowable, right? And the model, the true model, is probably a lot more complex than anything you have, probably, because it depends on other variables that you're not measuring and so forth. And so there's this notion of a distance between the estimated model and the true model in function space. And the AIC is an estimate of this distance. And it's an unbiased estimate, but because it is an estimate, it itself is subject to sampling variability. So if you went out and collected a new set of data from the same process and modeled it, you get a different value for the AIC. And as a result, you wouldn't necessarily expect the model that has the highest estimated AIC from your data is not guaranteed to be closest to the truth.
Have people ever done that? Like, try to look at the distribution of AIC values?
Yes, there's a really nice paper. I'll dig it up and post it. That took a. It was the model? Anyway, it's a simple model and a small number of data points, so that it was actually was possible to calculate the KL distance, which is the theoretical quantity, or the expected KL distance directly. And AICs were unbiased estimates, but the variability, it was also able to estimate the variability. And so the message that comes out of that is, if you're trying to do model selection with AIC, you shouldn't simply take the best model with the best AIC. You need to look at a family of models that have AICs that are within some distance of the best, which depending on sort of how conservative or liberal you are, tends to be maybe delta AICs of 5 or 6, and that, the conclusion is that the best model is within that set, and then how you go about picking among those is probably has more to do with, you're better off using a rule like, say, picking the most parsimonious model in that set rather than picking the one with the lowest AIC, or doing some kind of model averaging if your goal is prediction, rather than just picking one. So it's an interesting, model selection is an art, far beyond the realm of time series analysis, and the general conclusion between the statisticians who really understand the theory behind AIC is that the one thing that is definitely the wrong way to use AIC is to choose the model with the lowest AIC.
It just seems like that
which is what we want to do.
Right. It just seemed like that was the rule of thumb, and if you're going to, why not formalize that rule of thumb into some sort of optimization thing?
Yeah.
Makes sense though.
Yeah.
But if you are close enough, it really doesn't matter if you're choosing the wrong one. Not the best, but you are good enough, probably. So.
Well, it depends what you want to. It depends why you're selecting the model. If you're trying to draw inference about causal factors, then there may be two models with similar AICs that have very different structures, with very different independent variables.
But is that the case? Why are you comparing those models? If they are really different, you are probably trying to explain, or I don't know. If you have very different models that are similar in the output, you really don't. I don't want to choose between them because I'm building one or the other because some knowledge.
Right. So so the conclusion there would be that the data don't provide any information about which of these models is more likely to be acting. Right. It doesn't. If you have two hypotheses, and they essentially they both fit the data equally well, then rather than arbitrarily picking one, you'd say both of these are plausible, and the data don't support the distinction between them.
And
Yeah.
that takes me to another question, if
Sure.
we have time. How is there any way to compare like two time series based on what we have learned now? I'm thinking maybe the parameter or something that you could say these are really different, or no, they're not any difference between them.
Well, different in what sense?
I was thinking like variance analysis. Like if you have two set of data and you want to see if the mean is the same in both data set. I was thinking something like that in the time series.
They had the same previously.
Right, so you can ask whether they have the same, say, the same autoregressive structure or the same coefficients from the Riemann model or the same periodicity. And formal tests for that would probably be something like, fit model where you force both time series to have the same. You suppose it's an AR2 process. Force both of them to have the same coefficients, and look at the residual sum of squares versus a model where they're allowed to have the two time series are allowed to have different coefficients. So that sort of testing could be done. And in fact, informally as a first cut, you could, because the ARIMA fitting gives you standard errors on the parameter estimates, you can sort of eyeball those and see, if you get two, the AR1 coefficients from time series 1 and time series 2, right? If their confidence intervals overlap by a lot, then that would guide you to thinking there might be weak support for saying that they have different coefficients. So you can certainly do those kind of analyses. I don't think, I haven't come across them being done that often. So to a certain degree, you'd be kind of rolling your own hypothesis tests, in terms of thinking about a particular hypothesis you're interested in, and then sort of working out for yourself what the relevant tests would be, what the relevant approaches to that. There's not sort of if there's a standard framework for doing this, it's in such a small community that I haven't come across it yet. Okay. So, just to, one of the nice things about, one of the half nice things about this online textbook on time series analysis is it has a bunch of exercises. It doesn't give the answers, or if they do, they're somewhere hidden. But let's just kind of remind your brain of these rules of thumb for picking preliminary moving average and autoregressive components. There's a bunch of examples here of time series, the autocorrelation function, and partial autocorrelation function. So, for this example, what would you sort of, your tentative guess based on these patterns as to what P and Q would be from an ARMA model?
So let's start. I think that is an autoregressive model, if I remember well.
Okay, and why is that?
Because the PACF, the partial autocorrelation, PACF, decay super fast, while the other is slowly and with periodicity. And if I'm not
So even though the ASC shows there might be two, you go with progressive, the partial.
Right,
So
so the first
ignore-
rule of thumb is that if the ACF decays slowly and the PACF decays abruptly, then you go with the number of significant lags in the PACF. And remember that in the case of an AR1 model, you know, there's this sort of built into the model. There's this correlation between Z of t and Z of t minus 1. But because Z of t minus 1 is correlated with Z of t minus 2, you're going to get an observed correlation between Z of t and Z of t minus 2, which is, you know, why you still see these positive, why this is a kind of why we expect this to be an exponential decay.
And Bruce?
Yeah.
So when would you know to stop at the ACF instead of going to the P? So if the ACF graph would look like the PACF, then you would be satisfied? Is that-
Well, you always want to look at both.
You always, okay.
Yeah. So, let's see. So let's look at this.
Yeah.
This one. So what would you do with this one?
Doesn't it suggest moving average if the ACF decays abruptly?
Yeah. So the ACF decays abruptly, and you know, subject to the oscillations, the PACF is decaying exponentially. So that suggests moving average. Okay, so with one term. And how about this one?
It's two-term
Two terms of what?
autoregressive.
Negative.
So the first one is probably positive, the second one is probably negative. And this is a bit weird, right? I mean, it's not really an exponential decay. And that's probably because, yeah, there is something. Looking at this, I would say there's something more going on. There's kind of a long beat frequency where the variance expands and then comes down, expands and comes down, and that's not going to be captured by a simple AR2 model. So, you know, this is we have to remember that these models are not, you know, they are descriptive. They're not, first of all, they're not mechanistic. There's no sort of fundamental process in there. And second of all, you know, there could be all kinds of other stuff going on in time series. Let's see if there's some other interesting ones here. So this is, well, how about this one? Probably an AR2. That would be what I'd start with, but there's these things going on at really long lags. And there's also, there's a suggestion here of this may not be stationary, and if we differenced it, we might get a clearer picture. I think, yeah. if you, probably the best way to get some intuition about these is you can actually simulate models with different combinations of P and Q, and see not only what the ACF and PACF look like from a sample, but also get a sense of what the time series does, and the kinds of short-term non-stationarity that might arise from, especially from moving average processes that tend, if moving average terms are close to 1, the process time series can actually drift around quite a bit. Okay. So, given time series, so the ARIMA modeling is really, we have a time series and we just want to describe the kind of intertemporal correlation structure within it. We can use that to make short-term predictions. Obviously, you can't predict too far into the future with most of these models. But understanding those structures might also provide some insights into looking at potential mechanisms that may be generating those correlation patterns, moving average patterns. But the other place where these kind of models is useful is when we're doing a more mechanistic, or trying to fit some mechanistic models or causal models that relate multiple state variables, but those state variables themselves are being measured sequentially in time, right? So we have we might, if we're doing a fisheries analysis, trying to understand, how the stock dynamics work in a fish species, right? There's this notion that the recruitment depends in some way on the stock, and we normally expect it to be something that looks sort of like that, and so we have potentially beta. But these data are actually, usually what we have is each year we have a measurement of stock and we have a measurement of recruitment. So these data are actually collected through time. And some of these residuals are going to be affected by, say, oceanographic conditions that may be correlated through time, like the ENSO index or things like that. And so when we actually fit this model, if we then sort of turn around and take the residuals from this model and plot them as a time series, we may well find that this time series of residuals has autocorrelation structure or partial autocorrelation structure. So in which case, the ordinary least squares regression that we started with is likely to have bias parameter estimates, unreliable p-values, and all that. Okay. So the solution to this is to use, again, a generalized least squares, like we did with spatial analysis, but now the correlation that we're putting into the model is temporal rather than spatial. Right, so the model might say, so one of the standard stock recruitment models says that time for the recruits to develop, it might be stocking year T minus tau. So some, if this fish takes 3 years to mature, it's the number of spawners 3 years ago that generates a bunch of offspring, and then there may be some sort of density-dependent reduction in that number of offspring. And then the noise term is usually log normal. So we expect this to be a stochastic process with a log normal distribution. And so this is the Ricker model. And the nice thing about the Ricker model is you can make it into a linear model by taking log of both sides. Right? So you get log of RT equals log of F plus log of S at T minus tau minus B S at T minus tau plus epsilon. Right, so this is now a model that's linear in parameters with a normally distributed error term. Right, so this is why one of the reasons we like the Ricker model in fisheries analysis. But what we're interested in now is this residual, and so we can, to go from ordinary least squares to generalized least squares, we can add in a model for the residuals, right? We can say that the residual at time t is, say, b times the residual at time t minus 1 plus, or let's say, gamma. Right? So where the gammas are IID, right? They're independent. So this would say that the residuals from this model are an AR1 process. Okay, and so we can, using generalized least squares regression, we can simultaneously estimate this correlation structure and the parameters of the model that we actually care about. And more generally, we can say that epsilon is distributed with some Riemann structure. We have to, in practice, we would have to specify the P and the Q, and then we could ask the computer to estimate, if we said that the residuals were say a 2-2 process, we could say it will estimate the two autoregressive coefficients and estimate the two moving average coefficients. And I would say, and why don't I have a difference term in here? I remember that generically the Riemann models are PDQ, where D is the number of, or is the difference thing.
Because you are applying the random error in the same period. Yeah.
Well, what's the expected value, or the sort of unconditional expected value of epsilon? It's 0. Yeah. So it should at least, there shouldn't be a trend in epsilon. In fact, as long as you're using these squares, I mean, there might well be a nonlinear trend in epsilon, but you're certainly not going to be a linear trend in epsilon. If there is, and you're doing your least squares wrong. And so the way you proceed again is you start by fitting the OLS ordinary least squares model, and then you look at the residuals and treat them as an ordinary time series and say, is there some kind of autoregressive or moving average structure in them? And if so, then move on to this step. The tricky thing is that, you know, I was hoping to have a nice numerical example to show you guys. When I was playing, I had 4 fisheries time series on my computer that I was working with. 2 of them, there really was no there was no temporal structure in the residuals. The third one, there's just something weird about the data, that the pattern, the fitted model looks like that. And, you know, and there was significant autocorrelation to residuals, but the, you know, after, after taking that into account, I got a different model that, you know, looked like that. So clearly that's got, I mean, you know, there's a problem with the model, or yeah, there are really important other variables that aren't in the model in this case that it just doesn't make sense to do inference in that situation. And then the last one was curious because it was fitting. So I did the OLS regression. The residuals showed a autocorrelation pattern that was consistent with an AR1 process. So ACF declined gradually. There was one significant peak in the PACF. When I fit this model, it estimated a phi of exactly 1. And if I plotted not this view, but if I looked at recruits versus time, there was a declining pattern. The fitted value from the OLS model was sort of somewhere in there, and the fitted value from the generalized least squares model, which had a much lower AIC, was pretty much like that. So what it was doing was it was putting everything in, or it was putting a lot more. It basically was loading up the autocorrelated residuals. You know, on this plot, you know, the 2 fits weren't all that different, right? The parameter estimates weren't all that different, but the predicted values had a really different temporal structure, and I'm still trying to figure out what's going on in that. So it is, you know, if time series analysis is an art form, you know, generalized least squares with correlated errors is doubly so. So it's going to be another one of these things where if you have important correlation structure, you know, you can't really get away with not doing this, but it's not going to be a simple, you know, it's not a sort of thing where you know that the answer you get out makes sense in the way that you know the answer you get out is going to make sense when you do an ordinary least squares regression. So I will keep experimenting with that, and if I figure out what's going on, I will bring that back to you next week. So what we're going to turn to now is we've looked at spatial statistics, geostatistics primarily, which is point process, spatial point processes. We looked at time series analysis, but a lot of the we have observations and processing that's measured throughout space. We have observations throughout space and time, and we actually expect there to be dependencies in space and time. So here's just one example, or three examples really. So this is a space-time plot. So in this case, let's just look at this one. Space is one-dimensional. Okay, so this is actually a physics problem. I think it's a heat diffusion problem. So if we look at this one, which doesn't have very much noise, we start off at time 0 with this high concentration of heat in the middle of, say, a metal rod, and then we're looking at how the heat diffuses out across the rod through time. So we have space in one dimension, time in another dimension, and here's just a much noisier implementation of that same. These are actually simulations from a partial differential equation. And so we can see that there are correlations in both space and in time. When space is two-dimensional, which it usually is for the kind of problems we're interested in, it's harder to do this kind of visualization. But if you imagine stacking up spatial maps, and then you can see the patterns in space that we've looked at, and then at any one point you can drill down and see the patterns in time. So how do we deal with this? There's one of the readings that I posted on the Gotcha Space page kind of goes through a series of reviews, a series of publications starting in the 80s, where people were trying to tackle the spatial temporal analysis for acid rain, for analyzing acid rain. And at that point, there really wasn't much theory out there for these kind of analyses, and so it sort of traced the history of ever more complex ideas of how to do it. So the simplest thing you could do is say, if you're interested in if your primary is in the temporal dynamics. In this case, they were asking whether the acidity in precipitation was increasing through time. Simple thing you could do is just calculate a spatial average. So at each time point, just average the data, and then do a time series analysis of those averages. Right. So you basically get rid of the spatial information. You just treat it as, well, I suppose you could treat it implicitly. You're treating the spatial samples as being independent. Alternatively, you could model a time series at each location. Right, and this actually gets back to your question. So in this case, if I is an index of location, then we'd have a model for location I that says ZT at location I, suppose it was an AR1 process, has phi sub I times ZT minus 1 at that location, and then a residual for that location. So that just says, every place, there's a temporal process going on everywhere. It's AR1 everywhere, but we're going to assume we're not going to make any assumption about whether the fees are the same. And in fact, if you're interested in time trends, you're probably, this is probably actually going to be the first step is going to be to ask whether the time series is stationary. If not, you would difference it, and then you would have from the differences, mean the difference time series would tell you something about the rate of change at that, the average rate of change at that site. So that says basically that, you know, there's no information, you know, site J doesn't tell you anything about what's going on at site I. But if the sites are relatively close to one another and are being governed by the same forces, one might expect that at least in some aspects, they're similar. You could say that they have the same temporal structure. In other words, they have the same autoregressive coefficient, but that the errors are independent at each site. So in this model, ZT of I depends on ZT with this autocorrelation coefficient phi, which is now the same for all sites, but the residuals are still, oh yeah, there's a different time series of residuals at each location. Okay. So I call these simple approaches because, you know, they're conceptually simple and they're relatively straightforward to implement. So that, yeah.
On the last one, would that be, let's say, if you're looking at El Nino effects of flooding or something like that, would that fit that assumption? Saying, you know, they're all sites have precipitation increase around the same time frame, so, but independent errors at each specific location. Would that be a kind of a fit for that?
Well, that depends on whether El Nino actually can fit into the Barriga parameters or whether it fits into the errors.
Yeah, I was thinking on the
So,
not on the errors.
yeah. So, I mean, you know, if the structure, so it might, right? But it all depends. I mean, it depends on the process, on what you're measuring, and how rich this part of the model is in terms of its ability to pick up those temporal ephemeral signals. Well, I think we may talk next time. So the other approach is to, that's a sort of time series focus centric view. You can also take the spatial focused view. You can perform a spatial analysis at each time, right? And that's what people who are working with Sun did. And again, that says that, you know, it basically says that what goes on in terms of temperature at 4 a.m. in terms of spatial structure, there's no information, you know, it's independent or irrelevant what happened at 3 a.m. Right, we're just going to treat, isolate, or analyze each time period independently and not even think about what the intertemporal correlations might be. A somewhat more sophisticated approach is that uses all the, and so one problem with this is that, you know, if we only have a small number of sites, right, our power to actually construct a defensible variogram is limited, right? When you have, we're 8 or 16 sites, I think. So not a lot of, you know, not a lot of points in the variogram, and not a lot of confidence in the estimated theoretical variogram. So one way to get more, essentially to get more statistical power, is to analyze the spatial pattern across all of the time periods and assume that the variogram, the spatial structure, is constant through time, so that although the means, the actual values of, say, temperature are fluctuating from hour to hour, day to day, that the patterns of correlation between site A and site B are constant. Okay, so we fit a single variogram for the entire data set, spatial variogram, and then use this variogram, apply it to the time-specific data to make, say, if we're doing prebeam, to do time-specific interpolations. Okay, but by doing this, we may get a, this variogram. We're going to have more confidence in this, in the shape and value of this variogram than if we were doing it for each time step independently.
I'm not convinced of that. Why are we going to be more confident with the variogram if the variability in the distance is going to be higher? And the same distance, if you are taking this point once and again, you are going to have a set of points in the same distance, assuming that it's just one in that distance. So you are going to have a higher variability there, and then your variogram is going to try to represent all the points at the same time, while you know that variogram is not, it's the mean for everything and not necessarily for.
Right. So there's you could, if we're going to aggregate all the data, there's actually three ways we could think about doing it. Right. We could, and some of which make more sense than others. So we could aggregate the data, and then at each location just sort of calculate a mean value at each location, and then look at the variogram of those means. That sort of loses the power, and you lose a lot of information that way. The second way, which is I think what you're thinking about, is that we have, say we have 10 observations at each location, right? We have at that location a vector 10 observations. At location B, we have a vector 10 observations, and then we look at the the covariance between all of those, right? Which is what I think you're saying. And I agree that would just introduce lots more variability, especially if the whole field is shifting up and down. So if we think the whole field is shifting up and down, then what we want to do is we want to keep the time identity, right? So we're still going to, when we calculate the remember the variogram is based on the squared difference between the observation at location A and location B. But if we calculate those for time 1, we calculate that square difference between A and B at time 1. And then we calculate the square difference between A and B at time 2, and at time 3, and so forth. Okay, so that we are, in some sense, we're generating a series of observations of the spatial covariance at each time, and then we're going to look at the means of those covariances, right? Which is different than looking at the covariance among all pairs of observations across all time.
I'm kind of lost.
Well, think of it as the difference between a paired t-test and a two-sample t-test. Okay, so we have So remember how those work. So paired t-test, it says we've got um, for every observation of A, there's a sort of matched observation of B, right? And we can naturally look at the difference between them, and then ask about the distribution of those differences, and ask if the mean of those differences is 0. If we took those same data and did a 2-sample t-test, right, where we basically threw away the information about the fact that the observation came in pairs, our estimate of the mean difference, the point estimate would be the same, but our standard error would be much higher. Okay, so in this case, the analogous thing is, we're looking at these squared differences between observations at point A and point B. By linking the pairs of observations that are at a given time, that's going to give us, may or may not get a different estimate of the average covariance between A and B, but we're certainly going to have a smaller standard error in our estimate of that average covariance by doing that. But all of this is kind of, it's kind of just sort of fudging around. It's still, we're just fudging things, right? We're sort of saying, well, let's assume that, we're making some pretty arbitrary assumptions, like saying that the spatial structure doesn't vary in time, or that the temporal structure doesn't vary with space. And so what we might want to say is that, what we might expect is that there is simultaneously a temporal structure and a spatial structure. Okay, and so that, so that there actually is correlation between, not only is there a correlation between z of t at I and z of t minus 1 at I, but there might be correlation between z of t at I and z of t at j. And there might even be cross-correlation between z of t at I and z of t minus 1 at j. Okay? And so we can, and so since, we have looked at how to represent spatial structure or spatial correlation as the variogram, it's just correlate, or the squared variance, square differences as a function of distance. We have looked at correlations in time with the autocorrelation function, and that can just as well be turned into a variogram. In fact, we talked briefly about the variogram view of spatial pattern. And so we can combine those two empirically to look at a spatiotemporal variogram. Okay, so this is now a two-dimensional function. Along the x-axis here we have distance. So this is some data set. I think it's, I'm not sure which data. I can't remember what data set it was. It's some kind of the response variable is PM10, so some kind of atmospheric data. So we have distance. So this, if we just looked at this would be, this is the estimate of, this is the spatial variogram, right? So this is looking across space at comparing all the observations at a given time. Okay, and so the scale here, black is the lowest value at 10, yellow is the highest value at 60. So this is saying that, that the variogram, so it's sort of coming out of the screen, right? At longer distances, the variogram is higher, and So that's the spatial view. The temporal view here is if at spatial lag 0, right, we look across time, and this is time in days. And so what we see is here is that the variogram rises pretty quickly to about 50, okay, and then seems to asymptote. Okay, so this is, you can think of this as being, the variogram is conceptually, you know, the inverse of the autocorrelation function, right? So this is like a decaying autocorrelation. It's a variogram that goes up to an asymptote. And then, you know, and then you can see that, you know, if this is kind of, you know, the asymptotic variance at large space and time lags, you can see that, you know, it's sort of down here. If you look at a little bit of ways in space and a little bit of ways in time, they're still going to, you know, the observations are still going to be somewhat correlated. Yeah.
A little confused with the values because I was figuring out getting the data set right, but wouldn't the values go down over time, or
so this
what do the values represent?
So this is these values represent the variogram.
Okay.
Okay, so basically, you know, this would be so if we look at the spatial variogram, so we're looking at gamma as a function of h, the radius, the distance, right? It starts at 10 and is doing something like that. Here's 60. Okay. And then if we look at, and then the temporal variogram is a function of time, the time lag. We're still looking at gamma, okay, and it still starts at 10, and you know, maybe grows more quickly, and it seems to asymptote maybe at about 50. And basically, if we took this temporal variogram and flipped it upside down, it would have the same, roughly the same shape as the autocorrelation function. So, yeah. So here's actually, you know, here's the equation. So it's so for every value of h and t, for every spatial lag and every temporal lag, right? We calculate the expected value of these should be squared. So it should be the square difference. So z of x1 t1 minus z of x2 t2, that quantity squared. Given that the distance between x1 and x2 is h, and that the time difference between time 1 and time 2 is t, right? And then the expected values of those squared. And so that's, you know, empirically that's how we do it. So I mean, remember that, you know, in time, if we're sampling at regular intervals, you know, it's easy to define the pairs of times that meet this characteristic. When we're looking in space, typically, what we have is we have a distance bin, and so in this bin, we're looking at all pairs whose distance apart is between 75 kilometers and 100 kilometers. But then if we wanted to do any kind of analysis with this variogram, right, we have to fit some kind of model to it. Okay, and we can sort of get a sense of the kind of the structure of the model here. It's sort of going up in both directions. In this case, it doesn't look like there's a lot of interaction between the two, right? There's not a ridge going up in this direction. And the general shape, well, yeah. So it's sort of the temporal pattern is more or less the same everywhere, and then once you get out here, there's sort of no spatial pattern at high temporal legs. So, here's just another view. Actually, this gets to Juliana's question. So these are the spatial variograms at different temporal lags. Okay, so here's the time lag 0, the sort of the snapshot variogram, and you can see that it may not yet have reached a sill. And then here's a time lag 1, right? So this is the correlation between points that are locations that are separated by a given distance and separated by 1 day in time. Okay, so that's that's higher. And then if we were to map this sequence of points,